Hello, my name is Sean McGrath from the University of Limerick in Ireland, and today I would like to present a paper on predicting air quality indices from restricted sensor data by using deep neural networks. Outdoor air pollution is a leading health concern for the 21st century. Over 72% of the world's population is estimated to live in areas that have levels of air pollutants higher than the World Health Organization specific limits. This paper presents an inexpensive way to estimate Air Quality Index, or AQI, using deep neural networks. Traditionally, this index uses expensive monitoring sensors that evaluate maximum levels of these pollutants. Utilizing deep learning, an artificial neural net is employed to enable specific sensor data to be substituted or replaced while still obtaining accurate results. The presented findings demonstrate that one or more selected pollutants can be successfully removed from the input to the neural net while accurately predicting a correct estimate of AQI. Nowadays, people pay more attention to environmental problems. When we think of air pollution, we think of countries like China, India, Brazil. But air pollution has become one of the most serious problems globally. Indoor air pollution and urban air quality are considered to be the two most serious toxic pollutant problems in the world. Climate change is estimated to cost between 2 to 4 billion per year in health. A growing effort is being made to monitor the pollutants that degrade air quality. This typically relies on using expensive and complex sensors. Traditional prediction of air quality is a time-consuming task requiring bulky and expensive monitoring sensor sets that are inherently fixed and specific to specific locations. In this project, we will explore ways to reduce the cost and the number of sensors required for data collection using a mixture of cheaper supplementary sensors to detect air quality. And here we see some of the 6 most common air pollutants: ozone, carbon monoxide, sulfur oxide, nitrogen oxide, lead, and particulate matter. And here we see a percentage of each that you'd normally find in the atmosphere. Outdoor air pollution is one of the main health concerns. And we can see here that the list of air pollutants that are monitored on an average hourly basis, and the measurement and the values associated with each value. Some pollutants are more harmful than others, but these are the ones that are selected. So what is Air Quality Index for health? The Environmental Protection Agency Air Quality Index is a number from 1 to 10 that tells us what the air quality currently is in the station nearest you and whether or not it might affect you. A reading of 10 means that the air quality is very poor. A reading of 1 to 3 inclusive means that the air quality is good. And we can see that anywhere in between the air quality deteriorates. These air quality index are updated and every 5 minutes, and readings are presented. So what you're finding the fixed stations will monitor these values, do this calculation, and present a number for air quality index. So here in Europe, what we find is throughout Europe there's a distribution of air quality monitoring stations that will monitor these pollutants on an hourly basis and then indicate what the air quality is. The difficulty is that these are distributed in a wide geographic range. So if you're walking by a road where there's a lot of traffic, or you're cycling or whatever, then the air quality index that you may have on your phone or whatever may not reflect the air quality that's being read by the fixed monitoring station. And this becomes of concern. So these traditional air quality monitoring stations are expensive. The sensors in them are very accurate, right? And that is one of the advantages that they have, in the sense that but the geographical location of where these are positioned, they do not give a personal air quality index value of where you are particularly located. So the idea here is to see, can we look at two elements. One, can we take this data that's collected from these stations, and can we then predict in a different location, based on a limited number of parameters, what the air quality index would be? Or the alternative would be to see, could we predict air quality index for these fixed stations using less expensive sensors, and give you an accurate, so you could actually create a lot more lower cost fixed monitoring stations. So there's two different approaches that can be taken in this. Normally what people find is the air quality monitors that they have on their phones or their apps, or whatever device, you can buy dedicated air quality monitoring units that you can have. There's a number of issues associated with them. One, the air quality value that you're getting is read from a station that could be a number of kilometers away. So when you're reading an air quality index of 1 or 2 or 3 for AQI, then where you are, the air quality index could be up at 8 or 9. So it's not giving you a true reflection of air quality of your location. And the other thing with some of the personal dedicated air quality monitors, the accuracy of the sensors that they're using. The sensors may be uncalibrated and things like that, so they're not giving you a good indication of what is taking place. So there's a variety of sensors that you can buy. Some are quite cheap and some are expensive. The difficulty is if you're trying to provide global personal air quality monitoring, then this becomes a significant cost for people to buy these units, and therefore it doesn't really make sense. So the idea of this paper is to say, right, let's look at the fixed high quality sensors that are being used, see what the air quality values are, and then you're using neural nets to try predict, can we use cheaper sensors or less sensors. So here we have a heat map exploring if there is any correlation between the measured parameters in the data set. Some of the variables are independent, such as nitrogen oxide, and two sizes of particular matter. This can inform us of the choice whether to remove it later or not at the modeling stage. And then we have here the highest recorded pollutants in air will be monitored over a period of months, and we will use that to indicate is there different correlations at different times of the year and things like that. So the neural net architecture uses a 3 hidden layer model. So regression models have been applied to predict prediction in real world problems for many years. Neural nets are a growing solution to many complex tasks that require calculations with an estimate component, while being able to recognize the relationship between the large amount of data. So in this paper, we consider a feed-forward neural net using an activation function of the rectified linear unit variable for the neurons in the hidden layer. The model complexity is dictated by the number of hidden layer neurons, and the network found to offer the best results for this project was based on the using the range of the input sizes. The training is carried out using backpropagation algorithm. This trains the network by using continuous weight adjustments, minimizing a loss function that is a measure of deviations from the responses required in relation to the training set values. And here are some of the results that we've found, inspecting the predictions for how close the model was to the eventual outcomes. We can see that the removal of sulfur dioxide data as a parameter resulted in a high accuracy, with the estimated AQI being correct to nearly 94%. Sulfur dioxide is primarily formed in combustion from power plants and domestic heating that use fossil fuels. There has been a great reduction in these emissions since the introduction of smokeless coal, etc. Automotive fuels are also now low in sulfur. However, ship fuels use heavy fuel oil, and therefore you'll find that depending on the geographic location, you can actually even make some predictions, not on the value, but what's happening in a geographic location. It'll give you more input into, you can add that into the neural net. And some features that went into the construction of the AQI had varying amounts of variance in the recorded data. So the SO2 pollutants had very little variance in the data used in the training model. So as expected, there was very little effect of filtering out this weakly correlated feature. Sulfur dioxide remains a serious health concern in many cities, where the exposure causes acute and chronic airway respiratory problems. So the idea of using a number of cheap monitoring devices where you have personal sensors that are not as accurate as what you would have in fixed locations. So what we ended up doing is having a number of low-cost sensors distributed throughout the region, and these using LoRa were transmitted back to a gateway, and this information then, so you'd end up getting a heat map of the geographic location. And based on one fixed air quality monitoring station, you could then feed this information into your heat map and provide a contour map of what the air quality index would be in a region. So you'd have various different values that you would be monitoring and seeing how that would affect things. So this would be your heat map of the region where you actually are using a number of low-cost sensors, and then you would have a high air quality traditional station that would give you very accurate values. And between using these stations, the fixed value, and using the neural net, we were able to predict air quality values that were extremely high. So some future work. The low-cost sensor accuracy and reliability needs to be adjusted so that we can improve that. The idea of these low-cost sensors would be we should be able to distribute them, so therefore energy harvesting would be an advantage. And the neural net algorithms that we were using, so AI predictive models, would need to be improved. And then we wanted to extend the range to different geographic locations. And one of the co-authors works in USTC in Chengdu in China, and we were going to replicate the study that we have done there. Thank you very much.